Hello all, and welcome to week 3 of the Algebra 2 course offered by NPTEL. I am one of the TAs for the course. My name is Shubhajit Dash, and today we'll be discussing some problems which are loosely based on assignment 3. Now, some of the problems I have taken from assignment 3, and most of them I have made of my own. And I do hope that all of you are also attending Ajay Prajapati's TA session. So let's start. Yeah, Ravi. Hello. Ravi. Hello. Yeah, I remember you. So I'm audible, right? Okay. And yeah, okay. So I hope that you are doing well. And I also kind of remember Shomraggi, but maybe this is a different Shomraggi. Anyways, I hope I am audible properly, and yeah. So let's start discussing problems for this week. So, uh, so this week you guys have been learning about algebraic closures and uniqueness and existence of them, and also splitting fields, existence, uniqueness, etc. Right? So we'll be doing some problems based on that. So I hope that you guys are attending Ajay Prajapati's session as well. So he had been solving the assignment 3 problems, which is why I have sort of made questions of my own, but based on the content that you have been learning this week. So yeah, so let's start. Yeah, so my screen is visible hopefully to you guys. Yeah, so this is the first question. So which of the following statements are true? So every finite extension is always algebraic. Every algebraic extension is finite. Every algebraic extension of the form if adjoined with some element alpha, where f is a field, is finite, and D none of this. So which of the following 4 statements should be correct according to you? C will be correct, okay. And anything else? Oh, these are multiple choose questions, okay. So anything else will be correct according to you, or only C will be correct? So Ravi says C will be correct. Yeah, what about you, Shamraghi? Okay, so A and C should be correct. Okay, so yeah, so let's see. Oops. So A is definitely correct. There is no doubt about it. Why? Because A is correct. Why is A correct? Shamraghi, why is A correct? So so let K over F be finite, that is be a finite extension. Then let A be in K. You want to show that K is algebraic over F, which means that you want to show that every element of K is algebraic over F, which in other words means that every element of K satisfies some non-zero polynomial over F, right? That's the definition, right, of an algebraic extension, or of something being algebraic over a field. Isn't it, Ravi? Yes, what I am saying is an element is algebraic over a field means so assume f is a field and take an extension of the field, and you take an element a in the extension, then a is algebraic over the base field means that a satisfies a non-zero polynomial over the base field, right? That's the definition of an algebraic extension. So let k over f be finite, let a be in k. You want to show that a is algebraic over f, which means that you want to show that there is some non-zero polynomial over f which a satisfies, or one of whose roots is a. So how do you find such a polynomial? So it's very simple. Consider the powers 1a, a square, a cube, so on up to a to the power degree of k over f minus 1 maybe, or yeah, I think this, yeah. So now tell me, Ravi, the degree of k over f, you know, since k over f is finite, k, that means that k is finite dimensional as a vector space over f, which means that the degree of k over f is finite, right? Now the degree of k over f is precisely the dimension of k as a vector space over f, right? And how many elements have we taken here? 1a, a square, a cube up to a to the power the degree. Yeah, from how many elements are there in this set or in this list? 1a, a square, a cube, and so on up to a to the power k minus k up to a to the power the degree. How many elements are there? What is k? I didn't understand. What is k? K is to f is the degree, right? It's a natural number, isn't it? So k is to f is the degree. So how many elements have we taken? So assume k is to f is equal to n. That is the degree of k over f. No, is it n elements or more than n elements? So we have taken 1 a square up to a to the power n, right? So how many elements are there? This to from a to the power n. No. From a to the power n you have n elements, and you have one more element which is the multiplicative identity 1, right? So how many elements are there? Yes, n plus 1 elements are we have taken, and so these are n plus 1 elements, or what is n here? N here is the degree, so k is to f plus 1 elements we have considered. And what is the dimension of k as a vector space over f? It's precisely k is to f, right? And we have taken k is to f plus 1 elements in k, which means that they cannot be linearly independent. That is, in other words, they have to be linearly dependent over f, right? Since the dimension is k is to f and we have taken more than that, so which means that all these elements have to be linearly dependent over f, which implies that these elements 1 up to a to the power k is to f are linearly dependent, right, over f, which therefore implies that there exists elements lambda 1, lambda 2 up to, or let's say from lambda 0 up to lambda k is to f in the base field f, such that lambda 0 plus lambda 1 a plus, if you go keep on doing this up to lambda k is to f times a to the power k is to f, this is equal to 0, where not all lambda is a 0, right? Since we have linear dependence. right? And that precisely means what is this expression? This means that A satisfies a non-zero polynomial over F, right? Isn't it? Isn't it? Because what is a polynomial? The polynomial is lambda 0 plus lambda 1 x plus lambda 2 x square plus dot dot plus lambda n, or rather lambda k is to f. Think of k is to f as some n. So lambda n a to the x to the power n, right? This is your polynomial in fx, right? It's non-zero, and moreover a is a root of this polynomial, isn't it? Precisely because of this relation that we have here, right? Precisely because of this, right? So a is a root of this polynomial, which means that a satisfies this polynomial, which implies that a is algebraic over f, right? Is it okay? Yeah. Yes, yes. So that is point B. So we'll come to that. But anyway, so since A is arbitrary, A in K is arbitrary, so every element of K satisfies a polynomial, satisfies a non-zero polynomial over F, right? Hence K over F is algebraic. Right? So what about statement C? You said that C is correct. So why is C correct? C is correct because why is C correct? C says that every algebraic extension of the form f adjoint with alpha, where f is a field, must be a finite extension. So why is this correct? It's precisely because if f alpha is an algebraic extension of f, then what does this mean? If f alpha is an algebraic extension of f, then no, it means that every element of f adjoint with alpha is algebraic over f, right? Which means that in particular alpha is algebraic over f, since if alpha is an element of f adjoint with alpha, right? Right? You understand what f adjoint with alpha means, right? It is the smallest subfield. So assume f is a field, you have some large field containing f, and you take an element alpha in that large field. Then you can consider the subfield of that large field generated by both f and alpha, right? That is your f alpha. It is the smallest subfield of the large field which contains both f as well as alpha, right? So f alpha is algebraic over f means that alpha in particular is algebraic over f, isn't it? So alpha is algebraic over f, that is true if and only if f alpha is a finite extension of f. So it's trivially correct. So this is correct, as alpha is algebraic over f implies in particular, I mean this is equivalent, this doesn't just imply this statement, the fact that alpha is algebraic over f, this is equivalent. So this is true if and only if alpha is a finite extension of f. Right? It's as simple as that. Okay. It can be, but not here. If alpha is algebraic over f, then that is just equivalent to saying that f alpha is a finite extension of f, right? Why is that the case? That is precisely because f adjoint with alpha is isomorphic as a field. In fact, is f isomorphic. So there is an isomorphism from this to this minimal polynomial of alpha over f. So if alpha is isomorphic to this, right? This you have seen previously, I hope so. So if alpha is isomorphic to this as fields, right? And the second field that I have written here, which is fx modded out by the minimal polynomial, modded out by the ideal generated by the minimal polynomial of alpha over f. This is a field, and this is a finite dimensional vector space over f always, right? So that is why f alpha is also finite over f. That is, it's a finite extension of f. Now regarding your question, yes, f adjoint with some element can be an infinite extension as well, but that is only true in the specific case that alpha is transcendental over f. That is, if alpha is not algebraic over f, then f alpha will be an infinite extension of f, and converse as well. Okay, so if adjoint with something is algebraic over f, if and only if that something is not algebraic over f. Sorry, what I mean to say is, if adjoint with something is infinite over f, if and only if that something is not algebraic over f, that is, if and only if that something is transcendental over f, then the extension, this particular extension will never be finite. It will always be infinite. Anyways, so A and C are definitely correct. Now what about B? B is false, that every algebraic extension is finite. This is false. Why? B is not correct. B is not correct. As, why is this the case? Can you give me an example? An example of an algebraic extension which is not finite. Yeah, trivial extension is always finite. F is always finite over itself. Why? Because F as a vector space over itself is of dimension 1, right? So the degree is always 1. So that means it's a finite extension. But you need to come up with an extension which is algebraic but not finite. So this is what I leave for you as Q. So we consider an extension of Q. What is that? So Q adjoint with square root of primes. P is a prime. That is, what I am taking is this Q adjoint with root 2, root 3, root 5, root 7, and so on. So this is not, they won't be in Q, but this needs to be checked that the extension is infinite. Okay, so is not finite but certainly algebraic. So this will be algebraic precisely because all the square roots of primes are algebraic, right? Why is root 2 algebraic over Q? Because root 2 satisfies the polynomial x square minus 2 over Q, right? Which is a non-zero polynomial over Q, right? Yeah, so what you need, so this is what I leave for you to check, but a hint is this, that so you take Q root 2 over Q. What is the degree of this extension? The degree of this extension will be equal to the degree of the minimal polynomial of root 2 over Q, right? Now what is the minimal polynomial of root 2 over Q? It's x square minus 2, right? That is a polynomial of smallest positive degree which has root 2 as a root. It's x square minus 2, right? Yes, so this is the minimal polynomial, means that the degree of Q root 2 over Q is 2. Now what you do is you check that Q root 3, what you do is you adjoin root 3 to this extension, that is you take Q adjoined with root 2 and then you again adjoin root 3. Check that this has degree 2 over Q root 2. Okay, so over Q, by the tower formula or whatever you call it, over Q, this new extension Q adjoined with root 2 comma root 3 has degree 4. Now to the new extension Q adjoined with root 2 comma root 3, you again adjoin root 5, and you see that this extension as an extension of Q root 2 comma root 3 has degree 2, so that ultimately over Q this extension has degree 8, and you keep on doing this. Okay, so you keep on adjoining root of some prime one by one, and you see that the degree always increases by twice. Okay, so this, whatever this extension is, it contains sub extensions of degree 2 to the power n for every natural number n, which means that it certainly cannot be finite, right? That is, this as a vector space over Q is infinite dimensional. Okay. Okay, so this is your hint, but you need to sort of check it rigorously. But this is the hint, or this is the idea. Anyways, let's move on to the next question. So if F is a field and if A1 up to AN are algebraic over F, then F adjoint with A1 up to N is algebraic over F. So what you are given is this: you take a field F, you take some extension of F, and you take elements A1, A2 up to AN in that extension, which are algebraic over the field F. Okay. Then the claim is that F adjoint with all these elements A1 up to AN is algebraic over F. So if you want a picture of this, in case you are not comfortable with what adjoining elements or adjoining sets means, so the picture is roughly this. So this is your F, and let's say we have a different color. So this is your extension K, and suppose in the extension K you have some elements A1, A2 up to AN. Okay, so F adjoint with A1 up to AN means the smallest subfield. So you look at the smallest subfield which contains both F as well as A1 up to N. This is what F adjoint with A1 up to N means. I hope that you have seen this in the lectures. It has been covered, I believe so. Okay, so yeah, so what we are given is F is a field and we take elements A1 up to N in the extension K, and we know that these elements are algebraic over F. That means all these elements A1, A2 up to N, all of them will satisfy some polynomials, some non-zero polynomial over F, non-zero polynomials over F. So A1 satisfies a non-zero polynomial over F, A2 satisfies a non-zero polynomial over F, and so on. So these elements are given to be algebraic over F. Okay. It should be true that this smallest subfield containing both F as well as A1 up to AN, I mean all these elements and F, this should also be algebraic over F. This is an extension of F because it contains F, and moreover it has to be algebraic over F. That is, in other words, every element of this extension should be algebraic over F. Now why is this the case? This is true. So solution: true because A1 algebraic over F implies that F adjoint with A1 is finite over F, right? We know this. An element, as we saw before, an element is algebraic over F if and only if adjoint with that element is a finite extension of F, right? And in fact that we also know what the degree of the extension will be. The degree of the extension will precisely be equal to the degree of the minimal polynomial of A1 over F, right? Right? We saw this. Just now we saw this isomorphism that I have written here. F alpha is isomorphic to fx modulo the ideal generated by the minimal polynomial of alpha over F. So A1 is algebraic over F implies that FA1 is a finite extension of F, and we also know the degree of the extension. It will be equal to the degree of the minimal polynomial of A1 over F. And because A2 is algebraic over F, implies that A2 is also algebraic over FA1, right? If A2 satisfies a non-zero polynomial with coefficients in F, then A2 will also satisfy a non-zero polynomial with coefficients in FA1, right? Because FA1 contains F. That's very trivial. And this therefore means that F adjoint with A1 adjoint with A2, which is just the same as F adjoint with A1 A2, is finite over F, right? Over FA1, right? which therefore means that if adjoined with a1 a2 is finite. Yes. No, a1 is not contained in a2. A1 a2 are elements, right? I didn't understand your question. No, 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 that is not what I am saying. What I am saying is f of a1 to f of a1 you are adjoining a2. That is what you are doing. That is, you are looking at the smallest subfield of K which contains both f adjoined with a1 and a2. And that is just the extension f adjoined with a1 and a2. That is the smallest subfield of K containing f comma a1 comma a2. So anyways, so if adjoined with a1 a2 is finite over f a1, which implies by the tower formula, right? So why is this true? This is true by the tower formula, that is the degree of f adjoined with a1 comma a2 is to f, as you know, is equal to the degree of f adjoined with a1 a2 is to f a1 times if a1 is to f, right? This is what your tower theorem or tower formula says, right? That if you have a tower of three fields, so f contained in K contained in L, then the degree of L over f is equal to the degree of L over K times or multiplied with the degree of K over f. So this is what we are using here. Yeah, and they are finite extensions and all that. So this implies that f adjoined with a1 a2 is finite over f. And if you keep on doing this, so what you have is, so if you keep on doing this, what you have is f adjoined with a1 up to an is finite over f, right? Simple. Which implies that f adjoined with a1 up to an is algebraic over f. Okay. Because we know that every finite extension is always algebraic, as we saw in the part A. In question 1 part A, every finite extension is always algebraic. So using this, we can therefore say that f adjoined with a1 up to an is algebraic over f. Why? Since f adjoined with a1 up to an is finite over f, it has to be, it definitely has to be algebraic over f, right? Yeah. So that means that this is true. So let's move on to question 3. So this is something sort of I mean similar to what you have seen in Ajay's tutorial. So you earlier you saw that if you take the algebraic closure of Q, then it's definitely countable, right? The algebraic closure of Q is a countable field, right? That was a question I think that we have solved, isn't it? So yes, it will be true that since Q is countable, hence its algebraic closure is also countable, right? The main reason is that Q is countable. So we sort of do an abstraction of the same proof, or maybe I'll just sketch the idea again, that if F is a countable field, then its algebraic closure must also be countable. So what is the idea? The idea is very simple. So I'll just give you the steps, you complete them. So show that what do you show? Yeah. So show that, so this is step 1, that the set of polynomials over Q of degree less than equal to n is countable. Let's call this set let's call this set Pn. Okay, so what is Pn? Pn is the set of all polynomials with coefficients in Q and which have degree less than equal to n. Now since q is countable, this particular set will definitely be countable, right? Because this set will be in bijection with the set q power n. That is, the reason is that, Pn is equipotent to or is in bijection with the set q cross dot 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 cross q n times, right? You take this set, you take the Cartesian product of q with itself n times, that is, you take the product of n copies of q, then Pn will be in bijection with this, right? It's very simple. What is the bijection? So you take a polynomial x to the power, you take a polynomial let's say x to the power n plus half x square, and you map it to what? You map it to 1 comma dot 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 comma half, 1 0 0 dot 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 0 comma half comma 0 comma 1, right? This is the simple bijection. So whatever is that particular term, so you look at every term in the polynomial, you look at the degree of that term, and what you do is you map the coefficient of this particular term to the corresponding coordinate in the Cartesian product. So this will be a bijection, right? And q cross dot dot q, this is so let me write down the bijection in case. So a n x to the power n plus dot dot plus a0, you map it to what? You map it onto an minus 1 dot 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 up to a0. Oh, okay, so I need to take n plus 1 copies, yeah, because there are n plus 1 coefficients. So n plus 1 times, and this Cartesian product of q with itself n plus 1 times or any finite number of times is always countable. So this second set is countable as q is countable, right? So this is step 1. Step 2 is this that so what is step 2? Step 2 is therefore the set of all polynomials. Okay, so we have a notation for that, qx. So step 2 is qx is equal to the union of all pn's, right? In natural numbers, union 0, or sometimes people also like to think of 0 as a natural number. Anyways, that doesn't matter. So qx is the union of all polynomials of different degrees, right? That, yes. No. We are taking q, the product of q with itself n plus 1 times. The Cartesian product is being taken to be n plus 1 times. And this particular set of n tuples with the entries being in q, this is a countable set, right? Q is countable implies q cross q is countable, right? Yeah, so Pn has, so take an arbitrary polynomial in Pn, that is a polynomial of degree at most n, right? So what will such a polynomial look like? It will look like an x to the power n plus a1 x, an minus 1 x to the power n minus 1 plus dot dot plus a2 x squared plus a1 x plus 0, right? So how many coefficients are there? So an minus 1 up to a1. Yes, right? So this is an element in q cross dot dot cross q n plus 1 times, isn't it? So you map this polynomial onto this particular tuple. That is your bijection, right? Okay. Right? That is your bijection, and q cross dot dot q n taken n plus 1 times is countable. So that means Pn is countable. Now step 2 says that qx is the union of all such Pn's, which means that qx is countable, because you know that a countable union of countable sets is countable. therefore countable. Right? And step 3 is this, that what is the algebraic closure of Q? What do you know about the algebraic closure of Q? So it's an algebraic extension of Q, right, such that every polynomial over Q has, every non-constant polynomial over Q has all its roots in the closure, right, in Q bar, isn't it? That is the definition of algebraic closures, right? So E is an algebraic closure of F means that E is an algebraic extension of F, and every polynomial, every non-zero, every non-constant polynomial over F has all its roots in E. That is, splits completely over E into a product of linear factors. So Q bar therefore can be thought of to be the set of all roots of all polynomials over Q, right? So what is it? It is a set of all roots of polynomials over Q, isn't it? Right? And since the number of polynomials over Q is, so the number in quotes of polynomials over Q is countable, as we saw in step 2, and every polynomial has only finitely many roots, right? So that means Q bar has to be countable. Yeah, okay. Why did I work? Why am I working with Q again? Sorry, Q. The Q case has been covered. We are working a general case. So F. Yeah. So I should say F here, not Q. F is just a countable field. That is what you know. So the same proof will work. So n plus 1 times. And yeah. So this is F. And this is F bar, and yeah, so all roots of all polynomials over F, right, which can therefore be written as the union of so how should I write this? Okay, n in n union 0 union fx, a polynomial in Pn, that is fx is a polynomial of degree at most n, roots of fx. This is what it is. This is what f bar is, right? And since this set, so I should use a different color, this set is always finite. This Pn is a countable set, right? So you have that this entire thing is countable because you are taking a countable union of countable sets again. Okay. We didn't necessarily need step 2 here, but anyways, I mean, I just wrote it for simplicity. We can sort of avoid step 2 as well. But yeah, this is the idea. Okay, so maybe I'll just erase it and write it properly. I mean, if we want to use step 2, so union of fx in capital Fx roots of fx. Okay, so this set, this is finite and fx is countable, and you are taking therefore a countable union of countable sets, which is therefore countable. So the set of all roots of all polynomials over f is a countable set, and the algebraic closure is precisely f bar, right? Algebraic closure is precisely that, isn't it? Right? So you have taken a countable field f, you have taken a field f, you take an algebraic closure f bar, right? So what is f bar equal to? It is equal to the set of all roots of all polynomials over f, isn't it? Precisely because f bar is algebraic over f. So for every element of f bar, there will be some polynomial, non-zero polynomial over f which has that element as a root. And moreover, you also have this, that every polynomial over f has all its roots in f bar. So f bar is precisely equal to this set, right? So I should be a bit more precise here, and I should say that roots of polynomials over f contained in f bar. That is, we are taking those roots which are inside f bar. I mean, we always work with a fixed algebraic closure. So we are working with the fixed algebraic closure f bar here. You know anyway that any two algebraic closures of a given field are isomorphic. That is what the uniqueness theorem for algebraic closures states. But what we have, but to be very precise, we have fixed an algebraic closure f bar, and we are looking at the roots of all polynomials over f which are in f bar. The roots which are in f bar. Okay, so f bar is precisely this particular union. Okay, yeah, I think whatever I've written is a bit misleading now, because it sort of seems like we are only including those roots which are in f bar, but yeah, a better note, I think this would be, anyways, you get the idea. So what you are doing is you are taking polynomials over f, you are taking all their roots, and f bar is precisely the union of that, isn't it? So I think a way to fix this would be to sort of what should I say, to sort of have new notation for this. Let's see. Okay, so I'll maybe just omit this particular line. Yeah, so what are you saying? Yeah, yeah, you can sort of get around this problem by using some notation. So for every f, you fix a set, you have a set omega f, let's say, which is a set of all roots of the polynomial fx, roots of the polynomial fx, right? So you know fx has all its roots in f bar. So you just look at that, the subset of all roots of fx in f. F bar will be the union of all this. Okay. So yeah, you can get around this problem easily. The point is that it could happen that sometime. So what do I, so see, since you are initial, so I mean it's not wrong, since we have already fixed an algebraic closure f bar. That means whenever we are saying that something is a root of some polynomial over f, then that means that the root is inside f bar, because a root of a polynomial is something external to the, I mean which is not in the field, is something external to the field. So it's I mean it has to be in f bar here, because we have fixed f bar here. There is no other external field. Okay, so this is not ambiguous, I hope so, but in case you have problems with this, you can get around the problem by fixing more notation. Okay, so yeah, certainly this is countable. Now a bonus question is this: if you know some cardinal arithmetic, a bonus question is this: show that if what should I say, yeah, show that the cardinality of any field is equal to the cardinality of its algebraic closure, okay, where f is an infinite field. So the question is this, that if f is an infinite field, then the cardinality of the field will always be equal to the cardinality of its algebraic closure. So we saw this in the case of Q or a countable field. We saw that the algebraic closure of Q is countable. We saw just now that the algebraic closure of a countable field is countable, right? So this is true in general. If you have an infinite field, then the cardinality of that field will be the same as the cardinality of its algebraic closure. So just a bit of warning that this uses cardinal arithmetic. To prove this. Yeah. So this statement is certainly true. So this is true. Okay. So do you have any questions? Is it okay? Should I move on to the next problem?
So the cardinality in case of finite field, I can imagine, but in case of infinite field, the
No, in the case
uh,
of finite fields, this will not be true, right? Because the algebraic closure of a finite field has to be infinite. So we have a question right now that will sort of address this, that a finite field can, I mean, if you take the algebraic closure of a finite field, that has to be infinite.
that algebraic
So this statement is
infinite.
only true provided f is an infinite field.
Algebraic in case of infinite field, what it will be?
Sorry.
In case of an infinite field,
Yes.
the algebraic structure will that will make
Algebraic closure.
uh,
Yes.
that
What will not be closed? I don't understand. If you take an infinite field, every field has an algebraic closure, right?
yes, sir.
So if you take an infinite field, then it also has an algebraic closure. So suppose this is your infinite field and this is the algebraic closure. These two will have the same cardinality. That is what the statement says. Just as you saw that if you take q and if you take its algebraic closure, say the algebraic closure is countable since q is countable, right? So this is true for any infinite field. You take any infinite field, you take its algebraic closure, they will have the same cardinality. Okay, this is what the question says. Okay, so did you also study about algebraically closed fields? A field is algebraically closed if every polynomial, every non-zero polynomial over the field has at least one root in the field. For example, the complex numbers are algebraically closed, right? Right?
Yes, complex numbers are they are
Yeah. So what do you mean by algebraically closed? A field f is said to be algebraically closed if every non-zero polynomial over the field has at least one root in the field. That is, it has, you can, which is equivalent to saying that every non-zero polynomial over the field has all its roots in the field. Okay. Every non-zero yeah, I should be very precise. Every non-constant polynomial over the field has all its roots in the field. That is, it splits completely into a product of linear factors over the field. So you know that every polynomial with coefficients in C has all its roots in C, right? This is certainly not true for R, right? Why? Because x square, if you take the polynomial x square plus 1 in Rx, you know, right, that
it
x
is not
square,
closed.
yes, you know that x square plus 1 doesn't have any roots in R. So R is
But in
certainly
case
not algebraically closed, but C is algebraically closed. That is, if you take any polynomial, let's say you are taking this polynomial x to the power 100 plus I x to the power 90. I is the complex unit, imaginary unit. This is a polynomial in Cx. It will have all its roots in C. Okay. So C is algebraically closed, but R is not algebraically closed. So what is an algebraically closed field? It is just a field such that every polynomial over this field has all its roots in the field. Okay. Which is equivalent to saying that every polynomial over this field, I mean the only irreducible polynomials over this field have degree 1. They are on their the linear polynomials are the only irreducible polynomials over this field. So there are many equivalent statements of defining algebraically closed fields, and this is just one way. So now the question says that a finite field can be algebraically closed. So is this true or false? So if you take a finite field, a field which has finitely many elements, then it is possible for it to be algebraically closed. So this sort of answers your previous question. This will always be false. So why? Let f be a finite field with the elements a1 up to an. One of them is 0, one of them is 1, and so on, and there are other elements of the field, but that doesn't matter. Just assume that a1 up to an are your polynomials. I mean, they are all the elements of f. Okay, so what we do is we consider this polynomial plus 1 in fx. So do you agree that this is a polynomial over f? Because the coefficients are elements of f, right? The coefficients are clearly over elements of f. So this is a polynomial in the indeterminate x with coefficients in f, right? Now tell me, does this polynomial fx have a root in the field f? This polynomial that we have considered here, x minus a1 up to x minus an plus 1, can it have a root in f? Yes, yes. So assume if ai is a root, then f of ai will be 0, right? But what is f of ai? F of ai is 1, right? So 1 will be equal to 0, which is impossible, right? So fx cannot have any root. So fx has no roots in capital F, right? And thus we have found a non-constant polynomial over capital F which has no roots in capital F, right? And that means capital F cannot be algebraically closed, right? It's simple, right? Polynomial, yeah, yeah, yeah. So that is what I want to add as a remark here. This idea is close to Euler's idea for proving the infinitude of primes. So I have taken this idea from that proof. So you know or you know Euler's proof, right? For proving that the number of primes is infinite. So it was a very beautiful proof he has done in his elements. He had done in his elements. So what does the proof say? It says that assume that there are finitely many primes p1 up to pn. So 2, 3, 7, 5, 2, 3, 5, 7 and so on. Assume there are finitely many of them. And consider this number p is p1 p2 up to pn, this product plus 1. Okay, now this is greater than 1, which implies that there exists a prime q, prime divisor q, such that q divides this number, right? Isn't it? This is a natural number strictly greater than 1, which means that it has a prime factor, right? Hello. Yeah, so there is a prime which divides p, right? But that is a contradiction. Why? Why is it a contradiction? Because assume, yeah, we have assumed that p1 up to pn are the only primes, right? Q has to be one of the pi's. Q is equal to pi, and q divides this capital P, means that pi divides p1 up to pn plus 1, which is a contradiction, because this would imply that pi also divides 1. That's obviously impossible, right? So the idea that we have taken here in this proof is very close to this one. So yeah, but it's always good to ask questions like this. Why are we taking this? Why are we having this idea and so on? So anyways, the statement is false. The finite field cannot be algebraically closed. So let's move on to next one. So so C is a splitting field over Q of some polynomial fx in Qx. Is this true or false? This is very easy. So you take, so the statement is this, that the field of complex numbers is a splitting field over rationals of some polynomial fx with coefficients in rationals. So is this true or is this false? That is, there exists some polynomial fx with coefficients in Q which has C as a splitting field. Is this true or false? Okay, so what is a polynomial? First of, first of all, you know that what splitting field means, right? What is a splitting field? So what is a splitting field? Anyone? What is a splitting field? You guys have studied splitting fields this week, right? I'm not wrong, right? This is week 3 material. Ravi? But it was taught this week, right? Yeah, it was taught because I saw the questions as well. Thangeshwaran, do you know what splitting field means? Okay, that's quite bad. So splitting field of, so let me quickly recap what splitting field means. So assume f is a field and assume fx in capital Fx is a polynomial. So splitting field, so I mean whenever you talk about splitting field, you always talk about splitting field of some polynomial. Okay, so you always talk about splitting field of a polynomial over a given field. Okay, so you take a polynomial fx in Fx which is of degree greater than equal to 1, that is, you take a non-constant polynomial fx over a field f, then a splitting field of fx over f is, so what should a splitting field be? What does the name suggest? What should a splitting field be? No, that's wrong. See, what is our main idea? What is the main idea behind studying field theory? So what you want to do always is, you have a field, you have a polynomial over the field, and you sort of want to find out the roots of the polynomial, which might not be in this field, might be in some extension field, right? That is what you want. You want to find out roots of this polynomial. And when will you stop finding roots? When you are sure that all the roots of your polynomial have been found. Now, finding roots of a polynomial is equivalent to factorizing the polynomial into linear factors, right?
Yes, sir.
Right. So splitting field precisely is that field over the given field which has all the roots of the given polynomial, and moreover which is the smallest, which is in a way the minimal such extension of the base field which contains all the roots. Okay, so a splitting field of fx over f is an extension, so it is an extension E over f, that is E of the given, it is an extension E of the given field f such that in Ex, first of all, fx should have all its roots in E, which is equivalent to saying that fx should split completely into linear factors over E. So fx should be equal to x minus alpha 1 up to x minus alpha n, and let's say we add a a here. A is the coefficient, leading coefficient of f. So fx should be of this form: a times x minus alpha 1 up to x minus alpha n, where the roots alpha 1 up to alpha n of fx are in this field E, and a is obviously an element of the base field. Since a is a coefficient, it's the leading coefficient of the polynomial fx, it definitely has to be in the base field f, right? But that is not important. You can also work with monic polynomials. But what is important here is that all the roots of fx has all its roots in E. Okay. If that is fx splits completely into a product of linear factors, into a product of factors of degree 1. Okay. In this extended field, in this extension, in E, fx has all its roots. So fx splits completely into a product of linear factors. That is why we have this name splitting field. And secondly, you need something for uniqueness, right? Since we are talking about splitting field, it's not just something over which fx should split. Fx should split over it into a product of linear factors. Fx should factor over it into a product of linear factors. But moreover, something extra should be there, which is the fact that this extension E should be the smallest such extension. So that is, in other words, E should be f adjoined with alpha 1 up to alpha n. That is the smallest subfield of E containing both f as well as all these roots alpha 1 up to alpha n of fx. That should be E itself. So over E, that is in Ex, the polynomial should split completely into a product of linear factors. That is true. And moreover, it should be the case that over no proper subfield of E which contains f, the polynomial splits into a product of linear factors. So the smallest, or the minimal extension of the given field f, over which fx splits completely into a product of linear factors, over which fx breaks completely into a product of linear factors, should be E. It should not happen over something smaller than E, strictly smaller than E. Okay. E should be, so if you keep on finding roots on and on and on of the polynomial fx, if you keep on finding roots, then the first stage where you arrive at all the roots of the polynomial, that should be E. Okay, not something before that. This is what splitting field means. Okay, it is a minimal extension of the given field f in which the polynomial fx has n roots, where n is the degree of the polynomial. That is, in which the polynomial fx has all its roots. Okay, this is what splitting field means. Okay, now a couple of remarks about splitting fields is this. All of this was covered this particular week, but I think you guys need to study that. So go and study everything about splitting fields and algebraic closures and everything else. But I'll just give a few remarks. So this statement will be false, and this reason is this. So yeah, so as I said, that splitting field is always for a polynomial, right? If you take a polynomial over a given field which is of degree greater than equal to 1, so you take a non-constant polynomial over a given field, you talk about the splitting field of that polynomial, right? So splitting field is always for a given polynomial. You talk about the splitting field of a polynomial. Okay, so the no, that is not the question. The question is about C. C is a splitting field over Q of some polynomial fx in Qx. That is, whether there is a polynomial fx in Qx which has all its roots in C, and moreover C should be the smallest extension of Q, the minimal extension of Q in which this polynomial has all its roots. So nothing smaller than C should contain all these roots. Okay, so the first property is satisfied. Obviously every polynomial over Q has all its roots in C. Yeah, we always will have a smaller field containing the roots. No, that's not true. For example, if you take x squared plus 1 in Qx, the roots are I and minus I, which are not contained in reals, right? So the splitting field will actually be Q adjoined with I, the smallest subfield of C, which contains both Q and I. So Qi should be the minimal extension of Q, which contains the roots of this polynomial x square plus 1. That is, Qi should be the splitting field over Q of this polynomial. No, no, that is what I want to say. Qi will be a proper subfield of C. C over Q, C over, I mean Qi over Q has degree 2, but C over Q will have infinite degree, right? Because you know that there are many elements in C which are not algebraic in Q. For example, pi. Pi is not algebraic over Q. Pi can never satisfy a non-zero polynomial over Q, right? Pi is a transcendental number, right? E. E also is a transcendental number. Yeah, pi is not an element of Qi. That's true. Yeah, that way you can also say pi is not an element of Qi. So Qi is a proper subset of Q. Okay. So this will be false, but yeah. So the reason is this, that splitting field of a polynomial fx belonging to fx. Assume that the polynomial fx has degree n, then the splitting field of this is not what I want to say. What I want to say is this, that degree of splitting field, see, there is, you have a splitting condition in the definition of the splitting field, but moreover you have an added condition, right, which is that it should be the minimal such extension of the base field, right, in which the polynomial has all its roots, right? So that minimality sort of puts a bound on the degree of the splitting field. So degree of splitting field of fx, oops, what just happened? Yeah, degree of splitting field of a polynomial fx in fx, where the polynomial fx has degree n, let's say this is an n degree polynomial. So the degree of a splitting field of a given polynomial over a base field is an extension of the base field by definition, right? Because what you are interested in is always extending the base field to just include roots of the polynomial, right? You are interested in finding the roots of the polynomial. So splitting field is an extension by definition. So degree of this extension, degree of the splitting field of fx in the base field is at most n factorial. This was covered in the lecture this week. So if the polynomial fx has degree n, then the splitting field will have degree at most n factorial. You can prove this by using induction. Anyways, you can just go back and look at the lectures. But C over Q has infinite degree, right? As pi is transcendental. Or you can do this in a different way as well. For example, you can just look back at that particular example of an algebraic extension which is not finite. You adjoin with Q all the square roots of primes. This is an infinite degree. This is an extension of Q of infinite degree, right? And this is contained in C. So C has to be infinite degree over Q, right? So the point is that C over Q is infinite. I mean, it's an infinite degree extension, but the degree of a splitting field should always be finite. It can be at most n factorial, where n is the degree of the polynomial whose splitting field you are interested in, right? Isn't it? So C cannot be the splitting field. All right. Is it okay? Yeah. So C cannot be the splitting field of a polynomial over Q. C is an infinite degree extension of Q. but the degree of a splitting field of some polynomial, I mean the degree of a splitting field of any polynomial is always infinite, is always bounded, it's always finite. Okay, so do you guys know about the rank nullity theorem in linear algebra? Okay, so so we can, okay, so we can do this. So let f be a field and let alpha be an element in some extension of f such that alpha is given to be algebraic over f. Then if adjoined with alpha, I mean if adjoined with alpha, you know this notation, right? F first bracket alpha, this means that you are talking about the smallest subfield. So whenever I am looking at alpha, which is an element in some extension, I already have that extension. So the E is an extension, F is a subfield of this extension, and you take an element alpha in E. We can talk about F adjoined with alpha, right? Which is the smallest subfield of E which contains both F and alpha, right? And what is F first bracket alpha? This is the smallest subring of E containing both F and alpha. Okay, so these are two different definitions. I hope it was covered in class, but just to be very sure, I would just sort of write the definitions again. And please, from next week, please, I mean, just look at the lectures and then sort of we can, I mean, it would be better if we discuss like that. Okay. Yeah. So what is f alpha? If alpha is various, I mean, equivalent ways of defining. So it is, we can say that it is the smallest subring. Okay. So I should also mention the extension k. So you are given this situation, this is f and you have an extension k of f and take an element alpha in the extension. Okay, so f adjoined with alpha is defined to be the smallest subring. Okay, it is the smallest subring of k containing both f and alpha, which can also be, you can also check that this is equivalent, this is, I mean, this is an external description, you are defining f alpha from an external point of view, but internally what is f alpha? It is defined to be the set of all p alphas such that px is a polynomial in fx. Okay, this is what it is. So you take p adjoined with alpha such that px is some polynomial in fx. It's as simple as that. Okay, and so that is looking at all values of all polynomials in fx, values at alpha of all polynomials in fx. And what is f adjoined with alpha? I hope you know this because we have been dealing with this again and again in the previous problem. So if alpha is the smallest subfield, so that was a subring, now you want a field, so smallest subfield of k containing both f and alpha. So equivalently, what is this? Since it's a subfield, a ring, you know, for a ring you only have addition, multiplication, right? And because of addition you also have subtraction. So for f alpha to be a subring, it only needs to be closed under addition, multiplication, subtraction, etc., right? I mean, that's all that you need, addition, multiplication, subtraction. But for a field there is one more operation, right? Or rather, not an operation, yeah, you can say that it's an operation, but for a field, what I want to say is, for a field you also should have closure under inverses, right? Multiplicative inverses. So if alpha is p alpha over q alpha such that px and qx are polynomials in fx, and qx, I mean q alpha is certainly non-zero. Okay, So this is P alpha over Q alpha, says that Px and Qx are in Fx and Q alpha is non-zero. You can also define F alpha in this way. You can check that F alpha is this. Okay. So do check this. I mean, it's very apparent from the definition, but do check this, that F alpha is the fraction field of F adjoined with alpha. Field of fractions. You know, field of fractions of an integral domain, right? So this is so F alpha is the field of fractions of F adjoined with alpha. Okay, so now what we want to see is this: we are given a field F, we are taking an extension K of F, we are taking an element alpha in that extension, right? And alpha has been assumed to be algebraic over F. Okay, what we want to show is F adjoined with alpha is equal to F first bracket, I mean F third bracket alpha, that is the smallest subring of K containing both F and alpha is equal to the smallest subfield of K containing both F and alpha. So normally what you have is this, right? So F adjoined with, I mean F third bracket alpha, that is the smallest subring containing both F and alpha, should be contained in F first bracket alpha, that is the smallest subfield containing both F and alpha, right? This is obvious, right? By the internal descriptions, it's very obvious, right? Isn't it? Every element in F at for third bracket alpha is of the form P alpha for some polynomial P, and that can be written as P alpha over 1, right? Over the constant polynomial 1, P alpha by 1, and that is an element of F first bracket alpha. So F third bracket alpha is always contained in F first bracket alpha, right? But if alpha is algebraic over F, then these two are actually equal, which is really remarkable. So we prove this using our old sort of old friend from linear algebra, which is the rank nullity theorem. Okay. So tell me one thing, that if adjoined with alpha, so assume alpha is algebraic over F. This is given to you. Then we know this, that F adjoined with alpha is finite over F, right? That is, it's a finite extension of F. Is a finite extension of F, which is extension of, which basically means that, which basically is saying, I mean, the definition of a finite extension is that the dimension of F alpha over F should be finite, the degree should be finite, right? So this is, so that is F alpha is a finite dimensional vector space over F. Right? Right. Now, F third bracket alpha, that is the smallest subring containing both F and alpha, is a subspace, right? It's a vector subspace alpha, right? Why? Because it's closed under addition and scalar multiplication by elements of F, right? Isn't it? It's a subring, it will be closed under these two operations. So F alpha is a subspace over F of F alpha, and hence F third bracket alpha is finite dimensional as a vector space over F, right? It is also finite dimensional. Now we want to claim, or we claim this, that F alpha is not just a subring in this case. We have defined it to be the smallest subring containing both F and alpha. We claim that it is not just a subring, it is in fact a field. So claim is F alpha is a field. So to show that something is a field, to show that a ring is a field, what do you need to show? The ring already has one, so you don't need to worry about that. what do you need to show in addition? You need to show that every non-zero element is a unit, right? Every non-zero element has a multiplicative inverse, right? Yeah. So we claim that every non-zero element in F alpha has a multiplicative inverse. So let beta belong to F alpha minus 0 be a non-zero element. We need to show that there is some element gamma in this F alpha such that beta gamma is gamma beta is equal to 1. That is that is what would prove that F alpha is a field, right? That is beta has an inverse. So let beta be in this, beta be a non-zero element in F alpha. We just need to find out a gamma in F alpha in this, okay? Gamma which belongs to F third bracket alpha. So consider the map from F alpha into itself which sends any x onto beta times x. Now tell me something. So you have a mapping of F alpha into F alpha, right? What is this mapping? This mapping maps every element x onto beta x. So this is a mapping of F alpha into F alpha, right? Now tell me something. Is this map linear over F? Both are, so F alpha and F alpha, I mean it's the domain and codomain of this map are the same objects. They are the same vector spaces over F. So it's F alpha. So you have a mapping of F alpha into F alpha. That is a mapping of F alpha into itself. Is this map linear?
If it is a function, it should be surjective number 1 or 2 both.
No. We need to check that. This is what we are interested in finding. But is it linear? You cannot say it right away that it will be surjective, right? There's no guarantee that it will be surjective, right?
Linear condition is what?
Is it a linear map? Didn't you just tell me that you guys already know the rank nullity theorem in linear algebra? So for vector spaces, you have, if you have the rank nullity theorem, that means you must know what linear maps are, right? Isn't it? A linear transformation, a vector space homomorphism.
There is a linear transformation.
Yeah, so
It
is
a
this,
linear mapping.
yeah, is this map linear map? Is this map a linear transformation? Okay, so it preserves addition, right? Because x plus y is mapped onto beta x plus beta y, and c times x, where c is a scalar in F, is mapped onto beta times cx, which is c beta times x, precisely because you have commutativity in of multiplication in the field F. So this map, this map, this is linear, a linear map. This is a linear map, right? I mean over F linear map in other words. And both the domain and codomain, so this is a linear map from F alpha into itself, which means that this is a linear endomorphism of F alpha, right? So it's a linear mapping from F alpha into itself. So it's an endomorphism of F alpha, right? So both, and moreover F alpha is finite dimensional over F, right? So by rank nullity theorem, since this map is injective, okay, so sorry, I should be very, yeah, words don't commute in English language, so I should be precise. So this map is injective, that you are I mean it's okay, right? Why is this injective? Because assume x is an element in F alpha which is mapped onto 0, that means beta times x is 0, which means that either beta or x has to be 0, right? But beta has been assumed to be non-zero, and hence x will be 0. You are in an integral domain, so beta times x is 0 means that either beta or x is 0, but beta is non-zero. It has been chosen to be non-zero. You want to show that this non-zero element has an inverse, which implies that x is 0. So the map is injective, and hence by rank nullity theorem, yeah, I just lost my charge. Okay, so anyways, we can sort of complete the proof till pencil gets charged. But yeah, so the idea is this, that this particular map is injective, right? And the rank nullity theorem, what does it say, Ravi? Yeah, what is n, what is l, what is minus 1 here? It says that if you have a linear map P from a vector space V into a vector space W, and assume that V is finite dimensional over F, then the dimension of V is equal to the dimension of kernel, which is also called the nullity of the transformation, plus the dimension of the range, which is also called the rank of the linear transformation, right? So now look at this. You actually have a linear endomorphism, right? You have an arrow from F alpha to itself, right? Right? Yeah. Yeah. So you have a morphism from F alpha to itself. That is, you have an arrow from F alpha to itself, which is therefore an endomorphism of F alpha, and F alpha is finite dimensional, right? And the dimension of kernel is 0. The map is injective. So this arrow that you have from F alpha to itself, this morphism or this arrow that you have from F alpha to itself, this is an endomorphism which is injective, and by the rank nullity theorem, therefore what can you say? Complete the proof. What can you say now? This map is injective. So what does the rank nullity theorem say? Yeah. Continue.
Dimension is equal to
Rank plus nullity, right? Dimension of alpha will be equal to rank plus nullity, and nullity is 0 here because the map is injective, right? So the linear transformation's rank is equal to the dimension of F alpha over F. What is the rank? It's the dimension of the image of this transformation. So if the image, which is always a subspace of the codomain, subspace of F alpha, if the dimension of the image is equal to F alpha, that means that the image will be precisely equal to F alpha, right? So which means that the map is surjective as well. So this linear mapping, or this arrow that we have from F alpha to F alpha, this map is also an epimorphism. It's a surjection, which means in particular that one which is in the codomain is in the image as well, right? So there is some element in the domain, let's call it gamma, which is getting mapped onto 1, right? It's okay, right? So there is some gamma such that gamma is getting, that is the image of gamma is 1. So gamma is mapped onto 1. Now gamma is, by our definition of the map, it's mapped onto beta gamma, beta times gamma. So that means beta times gamma is equal to 1, right? So it's a beautiful proof. So beta times gamma is equal to 1 means that there is an element gamma in F alpha which is an inverse of beta. So we already have obtained an inverse of the element beta. So we do see this, that in this particular ring F adjoined with F third bracket alpha, every non-zero element has an inverse under multiplication, right? Which means that F alpha is actually a field. Okay. So this map is injective implies by rank nullity theorem, so this implies by rank nullity theorem that this map is also surjective. Which therefore implies that there exists a gamma in F alpha such that gamma is mapped onto 1, which is beta gamma. Yeah, so gamma is mapped onto 1, which implies beta times gamma is equal to 1, which implies that gamma is an inverse of beta. Thus, if third bracket alpha is a field, but we do know this, that this, what is F first bracket alpha, F adjoined with alpha, that is the smallest subfield containing both F and alpha, and it's the field of fractions of F third bracket alpha. But if F third bracket alpha is itself a field, its field of fractions will be itself, right? So which implies that, so this implies that F adjoined with alpha, which is the field of fractions of F third bracket alpha, is just equal to F third bracket alpha, because F third bracket alpha has been shown to be a field, and therefore we have this. So this is certainly true. This is certainly true. Okay. In fact, the converse is also true. That is, if F is a field, alpha is an element in some extension K of F, such that if third bracket alpha is equal to F first bracket alpha, then alpha has to be algebraic over F. So just a remark. I don't know if I have space. So remark. Converse is also true. Okay, so maybe I'll skip the next problem and move on to question 7. So any two finite fields of the same coordinate are actually isomorphic. I have chosen this problem because I believe you guys have studied, I mean, I know Ravi has studied group theory. I hope you also have studied group theory, and it will be very easy. So any two finite fields of the same coordinate are actually isomorphic. Is this true or false? What do you think? Yeah, it will be a bit twisted because you guys don't know splitting fields yet. But okay, so we are going to use one particular property, splitting fields. Any two splitting fields of a polynomial
The
yeah,
splitting field should be always unique, no?
yes, given field are isomorphic. Splitting fields are unique up to isomorphism. In fact, not only just an isomorphism, they are unique up to an if algebra isomorphism. So what I mean by this is that simply this, that suppose capital F is your base field and you are taking a polynomial fx over this base field, that is fx inside fx belonging to capital Fx, and you take any two splitting fields of fx, okay, then there is an isomorphism of one splitting field onto the other, which actually fixes the base field f. F is contained in these two splitting fields. Splitting field by definition is an extension of the base field. So there will always be an isomorphism from one splitting field onto the other, which fixes every element of the base field pointwise or element wise. So any two splitting fields of a polynomial fx over a given field capital F are actually F isomorphic. That is, there is an isomorphism from one splitting field onto the other, which fixes every element of the base field F pointwise. Yeah, so you are right. Splitting fields of a polynomial over a given field are isomorphic. Now, using this result, can you complete the proof that any two finite fields of the same coordinate are isomorphic? So this will be true. So let's see. So let capital F be a finite field. uh, do we need that result? No, I think let capital F be a finite field of order n. Okay, so my question is this: can you find out some polynomial? So you know that a finite field always has characteristic p, right, for some prime p, right? You know this, right? So capital F has characteristic p, or in other words, to avoid any kind of complications, let's just use simple words. So there exists a prime p such that if contains up to isomorphism, if contains zp, up to isomorphism, that is if contains a copy of zp, that is what I want to say. So there exists a prime p such that if contains zp or a copy of zp. Now can you find a polynomial over zp which has capital F as a splitting field? So I'll give you some hints for this. So just recall what is a field. What is a field, Ravi? A field is a ring with one, it's a commutative ring with one, in which every non-zero element is a unit, right? In which every non-zero element has an inverse under multiplication, right? So in other words, a field is a commutative division ring. That is, it's a commutative ring such that all the non-zero elements, if you take all the non-zero elements of the field, they form a group under multiplication, right? So if you just omit the zero from the field, whatever elements you are left with, that is the set of non-zero elements, is a group under multiplication. Okay, so it's a commutative ring in which the non-zero elements form a group under multiplication. Okay, so now tell me, consider this polynomial x to the power n minus 1 minus 1 in ZPX. You guys agree that this polynomial is in ZPX, right? What are the coefficients of this polynomial? The coefficients, there are two coefficients of this polynomial. One is 1 x to the power n minus 1 minus 1. And both, I mean 1 is always in every field. So it's in particular in ZP, right? So this is a polynomial over ZP. It's inside ZPX. Now tell me, so the claim is, every element of okay, just a minute. Yeah, every element of f minus 0, which is f cross, in other words, every element of f cross satisfies this polynomial or is a root of this polynomial. Why? Why is this the case? Why is every element of f cross a root of this polynomial? This is easy. I expect answers. Why does every element of f cross satisfy this polynomial? No, no, no. We are not. We haven't mentioned splitting fields as of yet. We don't even know what whether this polynomial has splitting field f or not. This follows very elementarily. Both of you guys have studied group theory, right? Hangeshwaran? Okay, so now it should be easy to answer. You know f cross is a group under multiplication, right? What is the cardinality of f cross? If the cardinality of f is n, if the cardinality of the field is n, what is the cardinality of f minus 0? And it's a group under multiplication. So you know that if G is a finite group and if you take any element A in the group, then A raised to the power of the order of G, of the coordinate of G, is always equal to identity, right? Now F cross has coordinate n minus 1, isn't it?
X raised to n minus 1.
If you take any element, so since F cross under multiplication is a group, hence a to the power order of F cross, the coordinate of F cross, which is a to the power n minus 1, this is always equal to 1 for all a in F cross, right? Which implies that a satisfies x to the power n minus 1 minus 1 for all a in F cross, right? Which implies that now the degree of x to the power n minus 1 minus 1 is exactly n minus 1, and F cross has exactly n minus 1 elements in it, right? Which means that this polynomial, I mean the set of all roots of this polynomial, is precisely F cross, which implies x to the power n minus 1 minus 1 has all its roots. Or maybe we can use smaller, I mean much better notation. So roots of x to the power n minus 1 minus 1, this set is equal to F cross, which implies roots of, if you just multiply x to this, so the factor x corresponds to the root 0, so roots of x to the power n minus x is equal to f. The set of roots of x to the power n minus x is equal to f, right? Now x to the power n minus x is what it's a polynomial over zp, right? And it has all its roots in f, that is, it splits completely into a product of linear factors over f. Moreover, is it possible that some smaller subfield of f contains all the roots of x to the power n minus x? No, right?
Yes, sir, no, there won't be any small.
Why? Because every element of f is a root of this polynomial. So if you discard an element, that means you are discarding a root of the polynomial, right? Which implies that the splitting field of x to the power n minus x in zpx, so splitting field of this polynomial over zp is equal to f, right? So first of all, this polynomial splits over f. Yeah, it looks like an alpha, it's actually x. So first of all this polynomial splits over f, and moreover f is the smallest, f is the minimal extension, right, over which this splitting happens. So over no proper subfield of f which contains zp, the polynomial can split completely into a product of linear factors. Over no proper subfield this can happen, because if you take a proper subfield of f containing zp such that x to the power n minus x splits completely into linear factors over that proper subfield, then that's a contradiction, right? Because once you take a proper subfield, it means that you are discarding some elements of f, but every element of f is some precise root of this polynomial, right? So the polynomial cannot have all its roots in a proper subfield. Is the logic clear to you?
Yes, sir, last.
Yeah, so what I am saying is, see, f is the set of all roots of x to the power n minus x, right? So every element of f is a root of x to the power n minus x, right? If you take a proper subfield of this, that means you are discarding some roots, right, of x to the power n minus x. So can this polynomial have all its roots in this proper red subfield? It can't, right? That means the polynomial cannot split over this red subfield. If it has to split, then the smallest or the minimal extension of zp such that over which it splits should be capital F, right? Not any proper subfield of capital F containing zp, right? Yes. So the smallest one or the minimal one over which the polynomial can split should be capital F itself, which means that capital F is the splitting field, right? Right? Yes, here the field itself, uh, the splitting field over Zp, splitting field of the polynomial x to the power n minus x over Zp. Okay, and what you already know, so what you have proved right now is if you take any finite field of order n, then that is a splitting field of some polynomial over Zp, right? That is what we proved. Any arbitrary finite field is a splitting field of some polynomial over Z over the base field. I mean over the prime subfield. Here we have assumed Zp is the prime subfield. Zp is contained. I mean for the prime p, fixed prime p, Zp is contained in F. This is what we have assumed. So the point is every finite field of order p to the power k something. I shouldn't. Yeah, I mean. Okay, so every finite field of order n, whatever that n is, that n always has a particular form, but forget all that. Every finite field of order n is a splitting field of some polynomial over the prime subfield, over Zp in this case, right? So, and you know already that by this red remark that splitting fields are always unique up to isomorphism, right? So if you take any two finite fields of the same cardinality, they will have the same prime subfield, and therefore both of them will be splitting fields of the same polynomial x to the power n minus x over Zp, right? We have proved that finite fields are splitting fields. Both of them will be splitting fields of the same polynomial, right? X to the power n minus x, right?
Yes, sir. And they will be isomorphic.
Yes. So now the statement follows. From the remark. I hope you guys know what prime subfield means. ZP means characteristic of a field, what it is. I hope you know. And so if two fields have the same cardinality, they will have the same prime subfield. You can prove this, that any finite field will have cardinality p to the power n for some prime p. So it can't happen that you have a field of order 6. That is impossible. A finite field will always have cardinality p to the power n for some prime p. It should be a prime power. Now if a field f has or cardinality p power n, that means the prime subfield contained in it is Zp. So if you take two finite fields f1 and f2 of order p to the power n, then both of them contain the prime subfield Zp, and therefore both of them are splitting fields of the same polynomial x to the power p to the power n minus x in Zp. And since any two splitting fields of a polynomial are isomorphic, so you take a polynomial and you take any two splitting fields of that polynomial, since they are isomorphic, hence any two finite fields of the same order or of the same cardinality are isomorphic. So this is true. Okay, so since you guys don't know what splitting fields are, but we sort of have introduced splitting fields. So I guess I'll end with this question today. Yeah, I'll end with this one. So this is a computation of the splitting field of some polynomial. Okay, so we take a polynomial over q, which is x to the power 4 minus 2. We want to compute its splitting field. Okay, so we have defined what splitting field means. It's defined to be the minimal extension of the base field. In this case the base field is q. So here it is a minimal extension of q such that x to the power 4 minus 2 splits completely into linear factors over this extension. And yeah, minimal extension I've already said. So it's the minimal extension of q over which the polynomial x to the power 4 minus 2 splits completely into a product of linear factors. Okay, that is in other words, it's the minimal extension over q. It's the minimal extension of q in which this polynomial x to the power 4 minus 2 has exactly 4 roots. 4 roots. Yeah, I shouldn't say distinct roots. That's again wrong, because you guys will soon study separability of polynomials. What is something called a polynomial being separable, which is when you require that the polynomial should have distinct roots in any splitting field. But an arbitrary polynomial can have repeated roots or multiple roots, right? And a splitting field is defined to be I mean, whenever you talk about number of roots of polynomial, you always include multiplicities of that root of the roots, right? So it could happen that some particular root occurs twice. That is alpha, and alpha is I mean, if you list the roots of a polynomial, it could be something like alpha, alpha, beta, 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 gamma. So roots can repeat. Okay. So of course, when we talk about the number of roots of polynomial, we always we include multiplicities, and a splitting field is just the minimal extension of the base field in which the polynomial has exactly n roots, where n is the degree of the polynomial. Okay. So you want to find the splitting field of x to the power 4 minus 2 over q. Now tell me something. Is x to the power 4 minus 2 in qx an irreducible polynomial in qx? Have you guys studied Eisenstein's criteria? This was covered in Algebra 1. So please go back and read that. So this is irreducible over q by Eisenstein. Okay, so it says that suppose you take a polynomial a0 x to the power n plus a1 x to the power n minus 1 plus dot 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 plus an in qx, and suppose p is a prime, p is some prime integer such that p doesn't divide a0, that p doesn't divide the leading coefficient, p divides a1, p divides a2 up to p divides an, and suppose further that p square doesn't divide an. If this be so, if all these conditions are satisfied, then this polynomial is actually an irreducible polynomial over q. Okay, this is what the Eisenstein's criteria says. Now here, if you take x to the power 4 minus 2, and if you look at the prime 2, then 2 certainly doesn't divide the leading coefficient, which is 1. 2 divides 2, which is the other coefficient, only other coefficient present here, and moreover 2 square doesn't divide 2, right? Or rather minus 2, I should say. Okay, so 2 square doesn't divide minus 2, but 2 divides minus 2, which basically means, therefore, by Eisenstein's criteria, that this polynomial is irreducible over q. Okay. So now what can you say? So this is irreducible over q. So if you look at the element 2 raised to 1 to the power 2 raised to the power 1 by 4, then this is a root of this polynomial, and x to the power 4 minus 2 is the minimal polynomial of this. Since it's irreducible and monic, therefore we know that this is the minimal polynomial. Is a minimal polynomial of 2 to the power 1 over 4 over q. So you know that minimal polynomial of an element, so assume f is a base field, k is an extension of the base field, and you take an element a in the extension, then provided that element a in the extension is algebraic over the base field, then the minimal polynomial of that element a over this base field is the smallest degree polynomial, is a polynomial of smallest positive degree which has that element as a root, right? This is what the minimal polynomial means. Now an equivalent way of defining this is this, that so you should so the minimal polynomial is a polynomial which is irreducible over the base field and which is monic and which has that particular element as a root. So 2 to the power 1 by 4 is a root of this polynomial. This polynomial is monic, and moreover by Eisenstein's criteria, this polynomial is also irreducible over q. So x to the power 4 minus 2 is the minimal polynomial of 2 to the power 1 by 4 over q, and hence by a previous result we know that q adjoined with 2 to the power 1 over 4 is to q. The degree of this extension will be equal to the degree of the minimal polynomial, degree of minimal polynomial of 2 to the power 1 by 4 over q, which is 4. The degree of the minimal polynomial is 4 because x to the power 4 minus 2 is the minimal polynomial. Okay. So but q adjoined with 2 to the power 1 by 4 is not the splitting field. You need to have more roots, right? You know that the roots of this polynomial are in C. Roots in C are roots of uh, x to the power 4 minus 2 in C are 2 to the power 1 over 4 certainly, 2 to the power 1 over 4 I, where I is the imaginary unit, because if you take 2 to the power 1 over 4 I power 4 minus 2, you get 0, right? You can calculate it easily. This is a root of the polynomial. And 2 to the power 1 over minus 2 to the power 1 over 4 and 2 to the power 1 over 4, I mean minus 2 to the power 1 over 4 I. These are the four roots of this polynomial in C. Hence we know by definition of splitting field. So so if you recall the definition of splitting field, did I write it somewhere? Okay, I didn't. I mean I wrote it but I erased it. So if you recall the definition,
In case of Q, see that
yeah, in that case C, if you take C, then since C is algebraically closed, so every polynomial over C will have a root in C, right? So the minimal extension of C in which this particular polynomial has a root is C itself. So the splitting field would be C itself. So C over C will be the splitting field in that case, and the degree would be 1. But the situation is drastically different in the case of Q. Okay, so hence splitting field of x to the power 4 minus 2 belonging to qx over q. So how did I define the splitting field? So f is a field, you take a polynomial fx in fx. A splitting field of this polynomial fx in fx was defined to be an extension e of f such that in ex first of all the polynomial splits, fx is equal to ax minus alpha 1 dot 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 x minus alpha n, where alpha 1 up to alpha n are in E. The leading coefficient is obviously in the base field. This is the first point, that the polynomial should split completely into a product of linear factors over this splitting field, over this extension, and moreover E should be the smallest such field. It should be the minimal extension. So E should be equal to f adjoined with alpha 1 up to alpha. E should be the smallest such extension or the minimal extension of f over which this happens. So E should be equal to the smallest subfield of itself, which contains both f as well as the roots of the polynomial. That is, E should be equal to f adjoined with alpha 1 up to alpha n. Now in this case, therefore, since the roots of the polynomial are 2 to the power 1 by 4, 2 to the power 1 by 4 I, minus 2 to the power 1 by 4 and 2 minus 2 to the power 1 by 4 I. Hence the splitting field of x to the power 4 minus q in qx over q is q adjoined with 2 to the power, just adjoin the roots with q and then you have the splitting field. Right? This is what the definition says, right, Ravi? Is it okay? No, C field is a field of complex numbers. We are just looking into the roots of this polynomial. The roots are inside C always, and the roots are this. Now C is not the splitting field. C is something large. Certainly the polynomial splits over C, that's okay. But for splitting fields, we also have a second condition, right? That is, the splitting field should be the minimal extension over which this polynomial splits, right? Yeah, we are working with the Q field only, but so the situation is this is Q, you have looked into C, the polynomial x to the power 4 minus 2 in qx, this is in qx, this polynomial certainly splits over C, but we need to find the minimal such extension of Q in which this splits, okay, and the minimal extension will be Q adjoined with the roots, that is 2 to the power 1 over 4 dot 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 2 to the power 1 over 4 I minus 2 to the power 1 over 4 I, okay. This is the splitting field. We only use the extension C to look at the roots, to find the roots. We know that these 4 are the roots: 2 to the power 1 by 4, 2 to the power 1 by 4 I, minus 2 to the power 1 by 4 and minus 2 to the power 1 by 4 I, right? Of what? Proper subfield of what? A splitting field is just an extension of the base field. It's the minimal extension of the base field in which the polynomial has all its roots. Now C is an extension that we can agree in which the polynomial has all the roots. But C is not the minimal extension. C is not the smallest extension. The smallest extension is this one. So this one will be the splitting field. Okay. This is the second point in the definition of the splitting field. Using this, we can say that this will therefore be the splitting field. The splitting field E should be equal to the base field adjoined with the roots. So here the base field in this situation is Q, and you adjoin with Q the roots of the polynomial. So this Q adjoined with 2 to the power 1 by 4, 2 to the power minus 2 to the power 1 by 4, 2 to the power 1 by 4I and minus 2 to the power 1 by 4I. This is the splitting field over Q of the polynomial. This is the smallest extension over which this happens. Okay. So from definition of splitting field, we know that the splitting field is this, and we just need to compute the degree and then we can stop. So we can you can check that this is equal to Q adjoined with 2 to the power 1 by 4 and just I. So certainly if a field contains 2 to the power 1 by 4 and I, it will contain 2 to the power 1 by 4, 2 to the power 1 by 4 times I minus 2 to the power 1 by 4 minus 2 to the power 1 by 4 times I, because a field is closed under addition, multiplication, subtraction, etc., inverses, etc. But the converse is also true, because if Q contains all these 4 elements, 2 to the power 1 by 4, 2 to the power 1 by 4 I, minus 2 to the power 1 by 4 and minus 2 to the power 1 by 4 I, then it will contain 2 to the power 1 by 4 and I, because a field is closed under division, multiplication by inverses. So these and these are the same, right? Now we already know, we already have, as we have seen previously, that this is equal to 4. So we have Q adjoined with 2 to the power 1 by 4 is to Q. This is equal to 4. Now Q adjoined with 2 to the power 1 by 4 is contained in R, right? It's a real subfield. But I doesn't belong to R. So I doesn't belong to this as well. And therefore, hence, Q adjoined with 2 to the power 1 by 4, comma I should have degree precisely 2 over Q adjoined with 2 to the power 1 by 4, right? You certainly know that I, the element I, is algebraic over Q because it satisfies the polynomial x squared plus 1. So I is also algebraic over Q adjoined with 2 to the power 1 by 4, right? If I is algebraic over a smaller field, and if you take a larger field containing that smaller field, then I will also be algebraic over the larger field, right? Because you can take the same polynomial again, isn't it? Isn't it? So I is algebraic over Q adjoined with, so I is algebraic over Q adjoined with 2 to the 1 by 4. What is one particular polynomial over this base field Q adjoined with 2 to the 1 by 4 that I satisfies? It's just x square plus 1. So this says that the minimal polynomial, which is the polynomial of smallest positive degree, should have degree at most I, right? I mean at most 2, right? Because x square plus 1 is a polynomial whose root is I. So the minimal polynomial of I over Q adjoined with 2 to the 1 by 4 should be at most 2. But it's certainly not 1, because if it were 1, that means if I would satisfy a linear polynomial over q adjoined with 2 to the power 1 by 4, what would that mean? That would mean for some elements alpha and beta in this extension q adjoined with 2 to the power 1 by 4, alpha I plus beta is 0, and that would mean that I is minus, so that would mean that I is equal to minus beta by alpha, which belongs to q adjoined with 2 to the power 1 by 4. That's a contradiction, because we just saw that I, which is an imaginary number, cannot belong to q adjoined with 2 to the power 1 by 4, which is a real subfield. It's contained in R. So I cannot satisfy a linear polynomial over q adjoined with 2 to the power 1 by 4, which in other words therefore means that I should satisfy a quadratic polynomial. That is, the degree will not just be at most 2, it will be exactly 2. It cannot be equal to 1. Okay. Thus by Tower theorem or Tower formula, whatever you call, the degree q adjoined with 2 to the power 1 by 4 comma I is to q is exactly equal to 4 times 2, which is 8. So 4 is because of this part. So let me see if I have a highlighter. No. Yeah, I do. So 4 is because of this part. This times the degree of q 2 to the power 1 by 4 comma I over q 2 to the power 1 by 4. So which we just saw is 2. Okay. So 4 times 2, which is 8. So the degree has to be equal to 8. Okay. Okay. So the degree is exactly equal to 8. And we are done. So the degree of the splitting field of x to the power 4 minus 2 over q has to be 8. If you consider this polynomial x to the power 4 minus 2 over q, it will have splitting field equal to q adjoined with 2 to the power 1 by 4 comma I, and that has degree 8 over q. So the answer will be 8. So answer equal to 8. Okay, so we can stop here and we can continue next day, but I would definitely ask you to please go and have a look at the previous lectures, so that it would be easier for you to understand and easier for me to explain as well. Okay, please do attend Ajay's sessions as well, Ajay Prajapati's sessions as well, and thank you. See you next week. Bye. Yeah.